use this when there are springs, there's gravity, and there is a motion. Okay, so let me give a brief overview before we start solving problems. So the formula which we are going to use is the principle of conservation of energy, which states that the sum of kinetic plus potential is sum of kinetic plus potential at another instant of time. So T is kinetic energy, V is potential, and 1, 2 are instances of time. So use this equation when all forces are conservative. Okay, and the examples of conservative forces are just two: gravity and spring. Conservative forces are forces where work done depends on final and initial state only. Okay, and you might want to know the non-conservative forces. They are 1, friction, 2, there could be a motor supplying a torque, motor torque, linear force, linear external force. So when you see these things in the equation in a problem, do not use conservation of energy, because energy is not conserved. Those forces, that friction force, the motor torque, linear external force, they add energy into the system, so you can no longer say that the energy is conserved. Okay, so let's see how to write the gravitational and spring potential energy. It's very critical that you get the right sign, otherwise you'll get the wrong answer. The gravitational potential energy is Vg is mgy. Okay, and when you're trying to find the energy, you always uh, first shoot for a datum, get a datum line, and then you can find the potential energy depending on where the particle is, or in this case a rigid body is, with respect to the datum. So if the body moves down, then the potential is negative. If the body moves up like so, then the potential is positive. Okay, if it's on the datum, then the potential is simply 0, because the displacement is 0. So again, something to remember is that the sign which you'll see for uh, Vg is going to be exactly opposite to the sign of work done. So what's the work done? When a particle moves down under gravity, when mg is downwards, yg is downwards. So it's multiplication of two negative signs. We're going to give you positive. So work done is positive, but potential is negative. When you go up, mg is down, vg is up. So positive, negative is negative. So work done is negative, but potential is positive. So if you try to remember everything, all those four signs, then it's going to be very confusing. What I recommend is pick one of the two. Pick either potential or pick work done. Remember the signs for either the work done or the potential, and then reverse the signs for the other one. So I always like to use potential. Remember the signs for the potential, and it's really when you move it up, the particle has, or the rigid body has ability to work, which means there's a positive potential. When you move it down, it's negative work because it's already done work to go down. So that's how I remember it. But feel free to use your own way to remember it. So I don't think we'll give you the signs in the formula sheet. You got to remember it yourself. Okay. The other thing which we'll use extensively is the energy due to a spring. Okay, so just like potential energy, you're going to decide a datum. Okay, datum would be some instant of time where you're going to use to measure the stretch. So let's assume that initially S0 is initial length of spring. And this is basically the unstretched length. Okay, we're going to assume that the spring is unstretched. Now when you stretch it, then you stretch the spring, there will be new length S1. If you compress the spring, is a new length S2. Okay, the potential here is going to be half k times, it's always the length of the spring, currently it's S0, minus the unstretched length, so it's S0, right? So it's going to be 0. The potential here is going to be half k S1 minus S0 square, and the potential due to compression is also going to be half k S1 minus, sorry, S2 minus S0 square. In other words, this length here is S1 minus S0, right? And this length here is going to be S2 minus S0. So remember, this is a very common mistake. You always have to subtract the rest length. People ignore that. Another common mistake is if you start off this way and then you compress the spring, so initial position here, final position here, the way people compute the energy is they do half k S2 square minus S1 square. Sorry, so half k S2 minus S1 the whole square. So that is wrong. You have to do S2 minus S0 square minus half k S2 minus S0 square. This is the change in potential going from here to here is going to be this minus this. It's not k S2 minus S1 the whole square. This formula and this formula, and subtract the two, will not give you the same answer, unless of course. No, I don't think it gives the same answer. Even if S0 is 0, it won't give the same answer. Okay, remember that it's always the stretched length minus the free length. This is the length when the force is 0. Length when force in spring is 0, or the unstretched length.
Could you write out like the section of 2 being S1 to S1?
Yeah, it's going to be, if you, so let me just write it down here. If free length is S0, if so, let free length be S0 if the spring is initially stretched to S1 and final stretch is S2, then change in potential from 1 to 2 is, so delta VE is half Ks1 minus S0 square minus half Ks2 minus S0 square. It is not half Ks2 minus S1 square. This is a common mistake, don't do it. Okay. Okay, so let's solve some. Well, I just have two problems today. Let's solve the problems. The slender 6 kilogram bar AB is horizontal, as shown, and at rest. And the spring is unstretched. So that's the free length of the spring in the current configuration. Determine the stiffness K of the spring so that the motion of the bar is momentarily stopped when it has rotated clockwise 90 degrees after being released. So this is the initial position. Finally, we would have something like this. Right? The rod is vertical, the spring is stretched, but it's at rest. So this is rest, this is rest. We're going to find K such that it will come to rest at that position. Okay, so since there are only springs and there's gravity involved, it's gravity. The better of using conservation of energy. There's no non-conservative forces here. Right? You could also actually solve this without using, you could actually use statics to solve this. or maybe not. How would you solve this without using conservation energy? Uh, so clearly you can draw the free body diagram of this with a force, and then that force is resisted by uh, the reaction forces at the pin joint. But if you try to do the force equilibrium, I think you end up getting, well, you get two equations, but there are three unknowns. And then if you oh, okay, so I think the way you solve this, if you did not use conservation energy, is you draw the free body diagram of this particular system when the spring is stretched by a little bit. Okay, the equation which you want to use is not F equals ma, but you need to use the equation which talks about moment about a. Okay, that equation is the best equation to use because you eliminate the forces at the pin joint if you take moment about a. So that equation will only have mg, it left k, and it will have an alpha. So you'll get an equation for alpha, and then you have to integrate the equation from, you have to integrate alpha from this position, theta equals 0, all the way to theta equals 90 degrees, given the fact that you know the velocity is 0 in this two configuration, and use that to solve for k. Okay? So what you're trying to do is you know the velocities here is 0, you know the velocity here is 0, you know the position here, you know the position here. So again, if you see, the key thing here is that velocity is a function of theta. That's what you're after. So when you have velocity as a function of theta, you want to use energy principles or principle of work done, right? What I've told you again and again. In this particular case, you're better off using energy because there are no non-conservative forces like friction. So this chapter, all questions you'll see will have that flavor of uh, uh, velocity is a function of displacement. And that's why I use those two principles. So as I said, one method is to use moment about A equals IA alpha and use the fact initial and final velocity is 0 to solve for k. The other method, and I can tell you that one will give you the answer, but it will involve computing an integral, while you could also use conservation of energy as v is a function of displacement. In this case, it's a function of theta. Okay, so let's use 2. T1 plus V1 equals T2 plus V2. Again, we use this because use this principle as there are conservative forces. Okay, so we all said T1, what's the initial kinetic energy? It's 0. Okay. However, if it was released from a non-zero velocity, then how would you find the energy of the system, of the rod? It's half IA omega square, right? Where IA is the inertia about A. You have to use the parallel axis theorem to find IA. What's the final kinetic energy? It's just 0, right? So we only have to find the potential energy, initial and final. Now, we're told that initially the spring is unstretched. So V1 due to the spring is 0, right? Because what's that? It's half k times the length minus the unstretched length. So the length is equal to the unstretched length, so it's 0. We have to find the initial gravitational energy. Now to find the gravitational energy, as I said earlier, we need to fix a datum. So we could choose any datum you like. We could choose a datum here, we could choose it here, anything you like. In this case, it just makes most sense to use datum either here or here, right? If this is the center of mass. So one of those potential will be 0. So let's just choose the datum to be here. So this is our datum for gravity. For gravity. So if that's the datum, what is the potential due to gravity? It's mg times distance from the datum, mg times yg, which is 0 because yg is right here. Okay, this is the new yg. Okay, now let's write the spring energy in position 2. So this is position 1, this is position 2. So we need to find the length of the spring here. What's that going to be? So let's see. I should. Let me just. This doesn't look well. This is 2 and this is 1.5. Let me just redraw this slightly and we can reduce the length of the spring so it looks realistic. Okay, that's better. That's 2. Okay, so we know that this distance is 1.5 and this distance is 2 meters. How do I know that? Well, this is 2 meters, this is 1.5. So when the rod is perfectly vertical, it's going to be 2 plus 1.5 is going to be the total distance from top to down. I also know this distance, right? It's the distance from A to B. That's 2 meters. So in order to find the spring length, it's going to be 2 plus 1.5, so 3.5 square plus 2 square, right? Pythagoras theorem. So I always have to take the length of the spring minus the unstretched length of the spring. We're told that the spring is unstretched in this configuration, so the unstretched length is 1.5. Half k of that. And then the final thing left is the potential due to gravity. So that's going to be mg times the displacement of the center of mass. Center of mass is here. So the displacement is length divided by 2, where the length is 2 meters. And since this is moving down, it's going to be negative. So in effect, we have from this equation 0 plus v1 is 0 equals t2, which is 0, plus v2 is v2s plus v2g. So 0 equals half k times 3.5 square plus 2 square minus 1.5 the whole square, minus mass is 6, gravity is 9.81, length is 2 meters. So we can solve for k. The answer is 18.53 Newton per meter. Okay, any questions? Questions? Okay, so I do have the stats for the other classes. So this class had a failure rate of 40%. The other big class, which meets at 10, the failure rate was 47%. And then the class which meets at 1 o'clock, okay, the system consists of a 60-pound and a 20 pound blocks A and B, so 60 and 20, and 5-pound pulleys C and D, so 5 and 5, that can be treated as thin discs. Determine the speed of block A after block B has risen by 5 feet. So you got to find speed of A starting from rest. Assume the cord does not slip on the pulleys and neglect the mass of the cord. Okay, so first of all, the only reason why this question is in chapter 18 and not in chapter 13, well, 14, is because we're told that these pulleys have mass and they are discs, they're given the radius. Okay? If I told you that these pulleys have no mass, then they would be particles, and then this would be a problem from the previous chapter. So just that thing changes if you are, but as I said, you can totally give this as a question in chapter 14 by saying this mass is 0. Okay. The other thing you want to note is that you're told to find, well, when this system in this B moves up, A moves down, you're going to find the velocity. So again, the key thing is distance as a function of velocity. So when you ask to find that sort of relation, you're better off using either principle of work done or conservation of energy. And you've got to choose which of the two you're going to use. In this case, there's only gravity acting. So all the forces are conservative, which means you've got to use conservation of energy. Okay, so conservation of energy will get you the answer. You could also do it the following way. You could draw a free body diagram, find tensions, relate the accelerations of B to A, right? And you see that the acceleration actually is constant, which means that you can use that formula, which is for constant acceleration. V equals V0 square equals U0 square plus 2AX. So you could do it that way too. So method 1. FBD and F equals MA. We'll get you the answer. The second method is conservation of energy. So let's use conservation of energy to solve this. Okay, so we would need to find the velocities of A and velocities of B. But because the system is a constrained system, velocity of A is related to velocity of B in a certain way. So we're going to try to find a relation between velocities of A and B, right? So this is going back to chapter 12 where you try to find how they are related by assuming a datum, drawing lengths like this, and then finding the lengths of the string. So let's do the kinematics first because eventually you'll need it. So length of cord, which is this cord, okay, I think you're better off choosing the datum here. So let's just use this as the datum because this length doesn't change. This is YA, this is YB. Okay, so let's just find the length of this cord. It's going to be YA plus YB plus YB. So YA plus 2YB equals length, but the length of the cable is fixed. So if you differentiate with respect to time, you get YA dot plus 2YB dot equals 0. Which means that the velocity of A is minus 2 times velocity of B. Another way of writing this is delta YA divided by delta T. This is definition of velocity. It's the rate of change of displacement divided by rate of change of time plus 2 delta YB divided by delta T equals 0. Or you can say that if you cancel off delta T, you can say that the displacement of A equals minus 2 times displacement of B. In other words, if YA moves the distance of 5 feet, then YV would move 2.5 feet downwards, right? Negative sign implies it's going to move in a direction opposite to that of A. So those are two expressions. Now let's use conservation of energy. Okay, the principle is T1 plus V1 equals T2 plus V2. So what's the initial kinetic energy? Starting from rest, so 0. What's the final energy? Well, let's see how many objects are there. There is A, there's B, there's C and D. All those things have masses, so we have to include the contribution due to all of those. A is a particle, so the energy of A is going to be half MAVA square. B is a particle, so MBVB square. Okay, particle only has translational energy. It doesn't have rotational energy. That's why I only wrote half mv square for both of those. C is a disk, so it rotates, but does it translate? Does C translate? Goes up and down? It doesn't. Just rotates. So it is only rotational energy. Rotational energy is given by half IC omega C square. So we got to find omega C. We don't know what it is. What about D? So D is a disk, so it's rotating, right? Because when you apply tensions, it's going to rotate. What about translation? Does it translate, go up and down? It does go up. So it has both energy. It has rotational energy and it has translation energy. Okay. Velocity of B is the velocity of this point, which is the same as the velocity of B. So I'm going to write it as VB square. This is total energy for D. Okay, so let's try to find what these things are. Uh, MAVA square. Let's try to solve everything in terms of VA. MA, MB, IC, ID, all these things are given, right? The only thing we want you to find is find relation A, VA, VB, omega C, omega D, and VB. So I'm going to keep everything in terms of VA plus, because VA is the unknown, half MB. I know VB from here, it's VA divided by 2 plus half IC. Omega C is angular speed of C. The angular speed of C is going to be velocity of A. This is the velocity of A time divided by the radius of the pulley A, or radius of pulley C, right? Plus half ID. Omega D is going to be velocity of B, right? This is velocity of B divided by the radius of pulley B. But we do not want to keep anything in terms of velocity of B. So we'll sub in the velocity of B. It's velocity of A divided by 2 times RB. So this is, and with a negative sign. So negative velocity of A divided by 2 RB square plus half MD negative VA divided by 2 square. Okay, so this equation has, the only unknown here is VA. VA is the unknown. So then I need to write V1 Okay, so I got to choose a datum. Well, let me just choose this as the datum. Okay, so V1 is going to be, look at the figure. So M A G Y A. So since A is downwards, it's going to be negative, right? Minus M P G Y B. Same reasoning. It's downwards. Y A Y B are unknowns. And then C is on the datum, so I don't have to worry about it. I need to worry about D. So it's M D G Y D. Okay, now there is that length of the string. So how would I get MGYB? Well, there is that length of the string, but really you'll see that doesn't really matter because it cancels off in the next step. So V2 is going to be the potential energy when P has moved up by 5 feet. In effect, A would have moved down by how much? 2.5. That's right. Yeah, it's sorry. If B has moved 5 feet, then YA would move 10 feet, right? 10 feet up because delta YA is 2 times. So I'm going to write the energy now. In the new configuration, YA would move up, negative sign, MBG. YB would move down, okay. The reason I wrote YB minus 5 is because YB pointing downwards is positive and P moves up, so it's YA minus 5, while A moves down, so it's YA plus 10, and then D is going to move YD plus 5. So what you need to do, if I'm out of time, let me just complete this. What I do is I'll take all these things and shove it in this equation, and what you see is that this YA will cancel with this YA, this YB will cancel with this YB, this YD will cancel with this YD. So this, when you take the difference, which will happen when you bring this to outside, you'll be left with no YA, YB, and YD. Okay, so you can get the value. So if you solve for solving, the only unknown is VA. You get VA equals, so let me write the equation. Just bear with me. I'm just going to write the equation and let you go. You get 475 equals 1.07 VA square, and you solve this, you get VA equals 20.54 feet per second. That's the answer. Okay, so I'll see you on Monday. We're going to start a new chapter. We're just 2 chapters away.